short explanation of that here. How do I know what numbered carbon each of these carbons are? Remember in organic chemistry, you had to number carbons based on where certain functional groups are, right? You wanted your alcohol carbon to be as low of a number as possible, and then you count from there. Same rules kind of apply here. You want to number your carbons where the most oxidized carbon is as low of a number as you can make it. The reason why I say as low of a number as you can make it, you'll see when we get to fructose. So let's look at glucose here. My most oxidized carbon is very easily identified as the anomeric carbon because it's attached to two oxygens. This one I'm going to call carbon 1, and I'm going to number all the other ones to make sure I cover all of my carbons. Carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6 is the one sticking out of the sugar. The one that determines whether you have a D sugar or an L sugar is the second highest one, in this case, carbon 5. It'll be a different carbon for ribose and a different carbon for fructose, but for glucose, galactose, allose, and mannose, it is carbon 5, the chiral center at carbon 5 that tells you whether you have a D sugar or an L sugar. Note that you do not have to identify given a picture, you do not have to identify given a picture whether you have a D or L sugar. You just have to know which carbon on there tells you whether you have a D sugar or an L sugar. Okay? For contrast purposes, let me try to find a picture of fructose. All right, let me zoom in here. All right. So fructose here is a 5-membered ring. Okay. Fine. Does it? Okay. Fructose here is a 5-membered ring. It still has 6 carbons in them. We need to find which one on here may potentially be the anomeric carbon, and what numbered carbon is the one that tells you whether it's a D sugar or an L sugar. So, going down here, where is the anomeric carbon? And the answer is it's the one bonded to 2 oxygens. So that is this one right here. It's the only one bonded to a hydroxyl and this oxygen in the ring, so this is my anomeric carbon on the right. What numbered carbon is the anomeric carbon in fructose? It is actually carbon 2, and this is why I gave you the definition of when you number your carbons, you want your most oxidized carbon to be as low of a number as you can make it. So here's what I mean. If I try to label this carbon carbon 1, let's try to number everything else. If this is carbon 1, that becomes carbon 2, that becomes carbon 3, that becomes carbon 4, and that becomes carbon 5. I have skipped this one, which you learned in organic chemistry you can't do. You're not allowed to skip anything. So this time I'm going to call this carbon up here carbon 1. That makes the anomeric carbon carbon number 2, 3, 4, 5, 6. I have now counted every carbon, and I made the anomeric carbon as low of a number as I can make it. Okay? This is how you number carbons in whatever sugar you are given. You try to make the anomeric carbon as low of a number as possible. So that's the first thing you should do when you see fructose. The next thing is which one here, and I don't remember what number I gave you guys earlier, but which carbon on here is the one that's going to tell you whether you have D or L fructose. It is always the second highest numbered one here. Well, let's see, 1, 2, 3, 4, 5. Oh, look at that. It's actually still 5 here. I probably misspoke earlier. It is carbon number 5 that tells you whether you have D fructose or L fructose. Again, you won't be asked to identify which one you have, just which carbon tells you that information. You can do the same thing with ribose. I'm not going to go over that because it's the same rules. Identify the anomeric carbon, make it as low of a number as possible, then count from there, and wherever is the second highest numbered carbon there, that is the one that tells you whether you have D or L configuration. Let me make sure I'm not forgetting anything there.
Josh, how do we know if it's D or L?
You don't have to know whether it's D or L, just that which carbon would tell you that information. That's it. Yeah, don't worry about actually figuring out whether a given structure is D or L sugar. You want your most oxidized carbon to be as low of a number as possible. Back in organic chemistry, you learned the rule that if you have like an alcohol attached to a carbon chain, you want that to be as low of a number as possible. Yeah, the most oxidized carbon is any carbon that's bonded to the most oxygens. That has the most bonds to oxygen atoms. That's why in organic chemistry you may remember that when you have a carboxylic acid on there, that becomes, you want that carbon to be as low of a number as possible. Yes, question? Yeah, for fructose it would be carbon 5. For galamine it was carbon 5. For ribose I think it's carbon 4, I believe. But yeah, if you draw it out and break it down like that, you can figure it out very easily. Okay.
And you said
Yes,
the same.
back there. How do you determine which carbon tells you D or L, right? The one, it's always the second highest numbered carbon on there. Which, if you're given a picture, you still have to identify which arrow is pointing to the second highest numbered carbon. So that's why we went over the procedure of numbering each of these carbons on here. Again, the bottom line here, and in fact, if you want, because I believe they actually even give you the numbers over here, you can choose to memorize that if you want. But the main rule is like that organic chemistry rule, where you want your most oxidized carbon to be as low of a number as possible. So that is simply whichever one is bonded to the most oxygens. Most of the time, it ends up being carbon 1. Fructose is the one time that your anomeric carbon ends up actually being carbon number 2. That's the only kind of special situation you have to worry about for this class. Okay. Number the rest of your carbons and you can figure out which one is your second highest one and you point to that one. Yes?
Do you have to know the structure for fructose too?
Yes, fructose, yeah, I guess I didn't write that down. Yeah, let me write that down. Yes, other than glucose and galamine, you need to know the structures for fructose and ribose. Okay. So make sure you study those structures as well. There's pictures of that in the notes.
What about the, for the aldose or ketose, like they're on the SI sheet, it's like the three-membered ones?
Yep.
What are those two?
That's the next thing I was actually going to go over. There's one bit of information that's important with that. And we'll go to that, and this is me jumping around a little bit. So, by name, not by structure, by name, it is important to know what the simplest aldose is and what the simplest ketose is. The simplest aldose, by name, glyceraldehyde. Sounds like aldose. It has an aldehyde group in it. Done. Dihydroxyacetone, not as easily memorized. Dihydroxyacetone is your simplest ketose. So glyceraldehyde is your precursor to all your aldose sugars, meaning glucose, galactose, and mannose, and ribose. Dihydroxyacetone is a precursor to fructose and the other ketose sugars you don't have to know for this class. Fructose is the only one you have to know. The only ketose you have to know for this class is fructose, and dihydroxyacetone is a precursor of that. So again, the simplest aldose, by name, is the only important part, glyceraldehyde. The simplest ketose, dihydroxyacetone. Don't worry about what they look like. Mm-hmm.
So for all natural sugars, they're like the D isomers, but are they based on D-glyceraldehyde, or is it just like generally D?
For aldoses, they depend on D-glyceraldehyde, but as you can see, dihydroxyacetone doesn't have a D or L configuration, so it's a little bit more complicated than that. So don't worry about that as a specific detail. In fact, about D versus L configuration, the only thing conceptually that matters from that is, you remember in amino acids you learned that all amino acids, naturally occurring amino acids, are in the L configuration. For sugars, it's a little bit more lenient than that. For sugars, the most common form of sugars in nature is in the D configuration. There are still a few that end up in the L configuration, but the most common form they take is in the D configuration, the sugars take. Okay. All right, we did that one. Okay. So,
you need to know like the one's the pyranose, one's like a fruitinose, and beetle, all that stuff.
For exam 2, you don't necessarily need to know that. For the final exam, maybe. So in fact, I would, if I was studying this and trying to get as much information as possible in as short of a time as possible, I would focus on just knowing the structures and what they look like rather than which one is pyranose or furanose or anything. I've given you guys shortcuts for that though, in case that becomes important, right? If it's a 5-membered ring, what term do you use to describe that? Furanose, starts with an F. 5-membered ring, furanose. If it's a 6-membered ring sugar, it is a pyranose. Okay.
Keto or acetyl don't need the. Hemi-keto or hemi-acetyl don't need the.
No. Hemi-keto, hemi-acetyl, don't worry about that for this exam. So 5-membered rings, you use the phrase furanose to describe them. 6-membered rings, you use the phrase pyranose. Let me see if I can find that. There we go. Pyranose. 6-membered ring. I keep forgetting what the next thing I'm going to go over, so 1 second. Okay, disaccharides. I'm not going to go over the specific details of it since we went over some really specific examples about disaccharides at today's SI session, which will be uploaded. It'll probably get onto YouTube about the same time the exam review will be. But let me just go to some pictures of some disaccharides. There's something wrong with it when I'm uploading it to YouTube. I really hope it works. If it doesn't work, I don't know, I'll have to figure something out. But every time I upload it, there's an error, so I'll keep trying with that one. Okay. All right. Disaccharides. The most important things when talking about disaccharides is not to memorize that this picture right here is lactose and this picture right here is sucrose. The most important thing is to be able to, and this is covered in detail at SI today, label the monosaccharides that compose the disaccharide, label whether they are connected via an alpha or beta link, and number the carbons that compose the link connecting the disaccharides to each other. I'll go over sucrose as the one example here. So if you're given this picture here, don't worry about labeling it as sucrose. You need to worry more about labeling it this long form. Or if you're given a disaccharide you've never seen before, you still need to be able to label it, label the long name of a disaccharide. So the first step is to identify the component monosaccharides. You won't get any color coordination on the exam, so you have to use the tips and tricks that we went over already. Let's look at the monosaccharide on the left here. Let's see, pointing up, pointing down, pointing up, pointing down. Very clearly, this one on the left here must be glucose because of that alternating pattern. The one on the right here is a 5-membered ring. That narrows down our options to either fructose or ribose. So what you can do is just count the number of carbons there are over here on the right. And if it has 6 carbons, it must be fructose. 1, 2, 3, 4, 5, 6 carbons. A 5-membered ring structure with 6 carbons in it is defined as fructose. Okay? So the first step in naming a disaccharide is label your monosaccharides first. So glucose on the left, fructose on the right. The next thing is to identify what type of linkage connects these two, whether it's an alpha link or a beta link. Well, you do so by looking at the very first the very first monosaccharide on the left, and figuring out which anomeric form it's in. So, where is the anomeric carbon on this sugar, on the glucose on the left here? It is this carbon right here. This carbon right here is the only one in the entire thing bonded to 2 oxygens. As illustrated here, I will remind you guys that these bends here, these like elbow turns here in this glycosidic bond, do not illustrate CH2s like they do in organic chemistry. This is just an old-fashioned notation to illustrate that this functional group is pointing down. Okay, it doesn't mean there's a CH2 at that corner. It's just to tell you that this functional group is pointing down. So, what is the CH2OH doing? It's pointing up instead. We learned when we were talking about anomers that if the anomeric carbon is pointing in if the functional group on the anomeric carbon is pointing in the opposite direction as CH2OH, we now know that this is the alpha anomer. It's in the alpha form, and therefore the linkage is an alpha link between these 2 sugars. So we've identified glucose as one monosaccharide, fructose as the other one, and they're connected via an alpha link. The very last thing is to report what numbered carbons actually compose this linkage between the two monosaccharides. We've done a couple examples of that. We now know that this anomeric carbon is carbon number 1 on glucose because of the numbering scheme we did earlier. And fructose, we even did that one as an example as well. We know that the anomeric carbon, which is right here on the left, fructose, I believe the one that we were working on earlier, the anomeric carbon was on the right. A very common mistake people do is they automatically assume, oh, the anomeric carbon is always on the right side of the sugar, I'm not even going to look. No, the anomeric carbon is always the one that is the carbon bonded to 2 oxygens, so check very carefully. For fructose in this drawing, the anomeric carbon is right here on the left here. It's the only one bonded to 2 oxygens, okay? It is carbon number 2 on fructose. If you want to know the reason why, go back to the explanation we did earlier for fructose. So our full name here, glucose alpha 1,2-fructose, describes what sucrose is here. Okay? Let's ask a couple other bonus questions here. Is sucrose a reducing sugar? No. Well, let's check why. We have to look to see if it has any free anomeric carbons. Well, here's anomeric carbon number 1. Anomeric carbon number 1 is a component of the glycosidic bond. There are no hydroxyls here, so it is not a free anomeric carbon on glucose. What about on fructose? Nope. No free anomeric carbons on fructose. The anomeric carbon right here is also a component of the glycosidic bond. Therefore, because there's no free anomeric carbons, it is not a reducing sugar. Yes?
So are all disaccharides are not reducing sugars?
Not necessarily. Good question. If you look at lactose here, short, quick explanation. One of the anomeric carbons on lactose is this thing on the right here. There is a hydroxyl on this rather than a glycosidic bond on here. So lactose actually has a free anomeric carbon, and it is a reducing sugar. So don't memorize that all disaccharides must be reducing sugars or that all disaccharides must not be reducing sugars. You go on a case-by-case basis and you look at their anomeric carbons. Yes, Jared?
There was a question about this, about which of the following does not undergo this type of reaction. I think it was with sucrose. Is it just because it's non-reducing sugar?
Yeah, I believe it's some solution called like Failing solution or something. So there used to be another term you would use to describe reducing sugar. Don't worry about it now, but if you're working on the practice exam, you'll see it because it was used to be there a long time ago. If you see the phrase that this sugar is oxidized by failing solution, it's just another way of saying it's a reducing sugar. So don't worry about that. If you see that on the practice exam but you can't find it in your notes, it's just another way of saying it's a reducing sugar. Yeah, so first is to identify anomeric carbon. So the question was, how to identify free anomeric carbon? First is identify an anomeric carbon. It's the ones bonded to 2 oxygens. A free anomeric carbon is you look at that carbon and you see if there's a hydroxyl attached to it. If there's anything other than a hydroxyl attached to it, it is not a free anomeric carbon. If there is a hydroxyl attached to it, it is a free anomeric carbon. Okay. All right, so we got to move on.
Do one of the sugars have to use their anomeric carbon to make the bond though? You can't have one with 2 for each.
In every example on here, yes. I don't know, though, every disaccharide in existence, so I can't say one way or the other. But in every example that is illustrated here, at least one of the sugars must use their anomeric carbon as part of the glycosidic bond.
Thank you.
Oh, small note here. If you are given a sugar that is drawn in the following form, actually these should be dashes. Are you guys having PTSD from organic chemistry? Don't panic, because this is just another way of illustrating whether something is pointing up or down relative to each other. In this example here, these are supposed to be dashes up here. CH2OH is pointing in a direction. We'll just say that dashes mean that they're pointing up. The wedge here is pointing in the opposite direction as the dash direction. So CH2OH is pointing up, therefore OH here must be pointing down, therefore this one must be pointing up, therefore this one must be pointing down, and we know this is the anomeric carbon. Someone tell me what sugar this is. It is glucose, and specifically it is beta glucose. Exactly. Alright, so if one or more sugars happen to be drawn in this pattern, again, don't panic. Just say to yourself that whatever color or shape up here is CH2OH pointing up. And then if you want, you can redraw the sugar where wedges mean that it's a functional group pointing in the opposite direction as CH2OH. And dashes mean that it's a functional group pointing in the same direction as CH2OH. Feel free to redraw it in the form you're more familiar with and try to answer the question. Yeah. No, yeah, you wouldn't have to. Well, I mean, you still could, right? Where's the anomeric carbon on this one? Still this one, right? The one bonded to 2 oxygens. So you could still call it carbon 1, 2, 3, 4, 5, and 6 here. Question? Yeah. Okay. I'll let you guys know if there is. I will not go into chair confirmation in detail right now. I cannot recall right now. If so, it may at most be one question. I will give you that. It would be the same questions that we've gone over. They just draw it in the chair confirmation instead. All right. I will give you. I'm thinking. Don't worry about chair or boat confirmation. I believe there isn't any on this semester. I'm only about 90% sure of that. I can't remember exactly. I will let you know if there's chair confirmation stuff, and I'll go over it at SI tomorrow and post a video on that. Okay? If there is chair confirmation on it. Okay. Gotta move on. What's the most stable anomer of glucose, alpha or beta?
Alpha.
The most stable one is beta glucose. The most stable one is beta glucose. That's good. You guys had a 50-50 shot at it, so it's better than a 25% shot. All right. Now I'll explain why. And I think this is about the extent of chair confirmation here. So let me go find a chair confirmation of glucose. Doesn't illustrate alpha and beta. Nope. I really don't want to draw the chair confirmation, so I'm looking for a picture. Alright, the closest one. This is the closest one here, but I think it only illustrates beta. Yeah. Okay. Short explanation for why beta glucose is the more stable anomer of glucose is that when you draw the chair conformation of beta glucose, all of its functional groups can be on the equatorial plane. I'm not going to explain why, because that's more of an organic chemistry thing, and you don't need to know why that is. Just that beta glucose, the orientation of beta glucose in the chair conformation can put all the functional groups in the equatorial plane. Alpha glucose gets very close. Alpha glucose, almost every functional group is in the equatorial plane except for one. The alpha anomeric hydroxyl ends up being axial. Not going to draw it, and you don't even have to know why that is. Bottom line, beta glucose is more stable because all the functional groups are equatorial. Yes?
Would he ever give us diagram and tell us which one would be the most stable?
No. If he talks about stability, it will be specifically glucose, alpha, or beta because it's a very unique situation compared to everything else. Okay. All right. Got to move along. Sugar derivatives. If you are given a sugar derivative, you are still able to identify it in a way by looking at some context clues. So this thing on the left here, let's take a look at it. Ignore the name. Obviously the name is glucosamine, but what happens if you forgot? If you forgot what this could possibly be? Well, let's look at the functional groups. CH2OH is pointing up, pointing down, pointing up. some new thing is pointing down, and that thing is pointing up. We now know that this alternating pattern must be glucose. It's not exactly glucose because this right here isn't a hydroxyl but an amine group. Given a multiple choice exam, you should be able to reason your way through it and figure out, oh, this must be glucosamine. It looks like glucose with an amine group attached to it. It must be glucosamine. Same reasoning could be applied to this one over here. This one, if you go through the functional groups, pointing up, that one's actually pointing up, and that one's actually pointing up, and then down. This actually looks very similar to galactose, except instead of a hydroxyl here, it's an amine group. You can reason your way through a multiple choice exam and say that this must be galactosamine. Okay? You can do this for any of the monosaccharides. If one of the functional groups is replaced, one of the hydroxyls is replaced with an amine group. Okay, so I'm not going to draw every example, but reason your way through some of these questions. These are all these things are linked to each other in very simple ways. All right, I just wanted to add that extra bit of information. Polysaccharides. You may be relieved to know there's not a lot that you need about polysaccharides for the exam. Let's see. In fact, the most important thing regarding polysaccharides is to be able to identify each one from each other. Just like with amino acids. There were 20 amino acids, but there were little shortcuts you could make where, well, I know that if there's an amino group in this amino acid, I know it's a basic amino acid, and that helps narrow down your choices. For polysaccharides, look for certain features in a polysaccharide to figure out which one you are looking at. We went over a couple today at SI. Amylose and amylopectin are two different versions of starch. You can identify these polysaccharides compared to all the other ones by first confirming that the polysaccharide is composed of glucose, and second, confirming that the glucose molecules are connected to each other via alpha linkages. Let's make sure that is true. I'm just going to look at this one in the middle right here. Here's the CH2OH. Here's the anomeric carbon right here. The anomeric carbon is pointing down, and the CH2OH is pointing up. They are anti to each other. This is an alpha link connecting all your glucose monosaccharides together. So, a bunch of glucoses connected to each other via alpha links is going to be amylose or amylopectin. Okay? It technically also is glycogen, but I'll explain glycogen in a little bit. So if you find a bunch of glucoses connected to each other with alpha links, you almost have your answer. How can you now tell the difference between amylose and amylopectin? Amylose is a nice linear chain of glucoses. Amylopectin has branches in them. That's about it. That's the only difference between them. They're both versions of starch, just that amylose is linear and amylopectin is branched. Glycogen, it turns out, looks exactly the same as amylopectin, but one extra difference. Glycogen just has more branches in it compared to amylopectin. That's it. I mean, that's why they don't even draw glycogen anywhere in your notes, is because it is actually indistinguishable from amylopectin, except it just has more branches. Branches are closer together in glycogen than they are starch. So, if you're given some polysaccharide, you can identify it first by looking at what monosaccharide it makes up that polysaccharide, and figure out whether they're connected to each other via alpha links or beta links. So glucose is connected to each other via alpha links, narrows down your choices to amylose, amylopectin, and glycogen. And to distinguish amylose, amylopectin, and glycogen, we've already went over. That you look at branches or unbranched.
So he has to give it to us like that. He can't do anything crazy like condensed formula or something.
No. Don't worry about like a polymer formula that I think sometimes you see in Orgo Lab. Don't worry about that here. Okay. Going down the list. Don't worry about dextrans. Dextrans, you do not have to worry about exam 2. If it shows up on the final exam, I'll talk about it then. But don't worry about dextrans. Other types of polysaccharides you can see, and don't panic if you see chair conformation here. is cellulose. Cellulose actually looks exactly the same as amylose did, except for one small difference. Rather than there being alpha links, like in amylose, cellulose is beta links. So if something is beta linked, it is cellulose. And if it's composed of glucose as well, I probably should have mentioned that. So it looks the same as amylose, meaning it's made of glucoses and they're connected at carbon 1 and carbon 4, but cellulose is beta linked and amylose is alpha linked. Where's chitin? Here's a picture of chitin. Chitin, in my opinion, is fairly easy to identify because it has a special functional group attached to it. Chitin is a polysaccharide of glucoses, but instead of a hydroxyl at this spot here, you have an amine, an amine plus a carboxyl group attached to it. Nothing else that you study will look like this. So chitin, if you're given a picture of chitin, should be very easily identified. Okay? Whether it's in chair conformation or Hawthorne projection, you're not going to see this functional group really anywhere else in your polysaccharide section. This arrangement of functional groups. Okay? So let's see. Amylose, amylopectin, glycogen, cellulose, and chitin so far. Question?
With the chitin, is that alpha linked?
Oh, yes. So cellulose and chitin are beta linked to each other. Here's a quick kind of trick there with alpha link versus beta link polysaccharides. If it is an energy storage polysaccharide, meaning starch and glycogen, they are alpha linked. If it is a structural polysaccharide, such as cellulose and chitin, they are beta linked to each other. All right. So structural is beta linked. Energy storage polysaccharide is alpha linked. Other important polysaccharide category, glycosaminoglycans. Glycosaminoglycans really don't look like anything else in the polysaccharide section, so they should be pretty easily identified. Don't worry about labeling whether this is specifically heparin or chondroitin 4-sulfate or whatever that is. It's more important when if you're given a picture to know that it is the category of glycosaminoglycan. So how do you identify that? 1. A glycosaminoglycan is a repeating disaccharide. Notice each of these examples, they only show you 2 sugars. They're trying to tell you that those 2 sugars are repeated over and over and over again. So if you have a repeating disaccharide, that's the first thing the first clue that what you have is a glycosaminoglycan. The second clue is some type of amino group. Okay, but we already saw that chitin has an amino group, but that's why you have to go through all 3 clues for glycosaminoglycan. Clue 1 was repeating disaccharide. Clue 2 was some type of amine group. Clue 3 is negatively charged functional groups. Okay? If whatever structure you are looking at is a repeating disaccharide, has an amine group somewhere, has negatively charged functional group somewhere, whatever you are looking at is a glycosaminoglycan. Okay? Don't worry about identifying any of these specific names. Even if you see these specific names in a multiple answer choice thing, don't panic. Whatever question that is asking is still answerable by just being able to identify that your given picture is a glycosaminoglycan. Okay? So that's it for glycosaminoglycans. One more category of polysaccharides that is important is glycoprotein. So, glycoproteins are proteins with sugars on them. That's what the term glycoprotein means, are proteins with sugars on them. There are 2 categories, an O-linked glycoprotein and an N-linked glycoprotein. An O-linked glycoprotein is sugars attached to either serine or threonine. You may have to go back and study a couple of your amino acids to remember which one it looks like serine and which one looks like threonine. But if you are given 1 or more sugars that's attached to an amino acid, either serine or threonine, you classify that as an O-linked glycoprotein. If instead your sugars are attached to asparagine, that is an N-linked glycoprotein. Okay? So these are listed on here, so you can look at this section of the notes to reconfirm this. But O-linked glycoproteins attached to serine and threonine, N-linked glycoproteins attached to asparagine. What do glycoproteins do? Well, there's a nice slide that explains all that for you. They alter the properties of a particular protein, either stabilizing it or giving it some type of signaling function. The ways it can stabilize it or alter its signaling function has to do with this slide right here. At least this is the one example they talk about in detail. N-linked glycoproteins can be broken down into 3 categories. A high mannose configuration, or a complex configuration, or a hybrid configuration. If you're given any one of these pictures, you may be asked, which configuration do you have? The high mannose one is the easiest one. It's made of a bunch of mannoses. The hybrid one, in my opinion, is the second easiest one. The hybrid one branch is made of a bunch of mannoses, and the other branch isn't. That's it. It's a hybrid. The complex form is the one that has sialic acid attached to the end of it. Okay? So the complex N-linked glycoprotein category is the one with sialic acid attached to it. What's important about sialic acid? The most important thing about sialic acid is if a glycoprotein has sialic acid attached to it, it's a signal for protecting that protein to prevent it from being degraded. If this sialic acid tip, if either one of these is removed from the glycoprotein, it's a signal for the cell to degrade that protein. So sialic acid is a very, very important regulatory component of glycoproteins because its presence on the glycoprotein prevents the degradation of that particular protein it's attached to. If it's missing, it's going to get degraded. And that's it for 7b. Okay. So I know it's 8:30. I'm going to continue anyway. Feel free to stay if you want, but obviously this is all optional anyway. If you need to leave, you can leave. I will continue. Unless we're getting kicked out of the room. I don't know. I can't tell.
We'll find out later.
I guess we'll find out. All right. I don't know. There are 9 classes, right? Okay. So, we haven't gone over Chapter 8 stuff yet in SI, so I'm going to cover the most important things here. And then I'll cover it in detail at SI on Thursday. All right. So, Chapter 8a describes the different types of lipids that you could have, that you see in biochemistry and in biology, the different categories of lipids. And so the most important thing you guys need to be able to do is, if given a picture of a lipid, to just figure out which category of lipid it belongs to. Not to necessarily name the specific lipid, but just what category it is. So we're going to identify a couple examples here. Fatty acids are your first category of lipid. Fatty acids should be the easiest thing identified because, zoom in here. A fatty acid is composed of a carboxylic acid end, that's the acid part, and a long non-polar chain of carbons and hydrogens. That's the fatty part of fatty acid. There are 2 categories of fatty acids: saturated fatty acids and unsaturated fatty acids, and you can clearly see the difference between them. Saturated fatty acids, only single bonds. Unsaturated fatty acids have at least 1 double bond. Okay? That's how you can tell the difference between saturated and unsaturated fatty acids. Let's see. More importantly than that, how do the double bonds affect the melting point of fatty acids? These are saturated. Here's some unsaturated ones. Conceptually speaking, think back to those intermolecular forces that we talked about in exam 1. That a lot of molecules are held together by either hydrogen bonds or van der Waals forces, things like that. When we are looking at saturated fatty acids, look at this structure on the left here. See, saturated fatty acids can be packed very close together because these nice long linear chains of carbons and hydrogens can fit very close together because they are nice straight lines. There's a lot of intermolecular attractive forces, London dispersion forces, keeping these things together. So that strong intermolecular attraction actually makes it so that saturated fatty acids have a higher relative melting point. It's why saturated fats happen to come as solids more often than not at the grocery store. Saturated fats, like butter and all that, are in a solid form. Meanwhile, unsaturated fatty acids, because of those double bonds, you have what is called these kinks or bends. In the shape of an unsaturated fatty acid, and look at that, you are not able to pack them as closely together. So for unsaturated fatty acids, because of the double bond nature here, you're not allowed to put them very close to each other. There isn't as strong of an intermolecular attractive force between them. Thus, unsaturated fatty acids have a lower melting point. So melting point of fatty acids depends on two things: the number of double bonds in there and the number of carbons in there. The more carbons you have, the longer the chain is and the stronger the attractive force is. The fewer carbons you have, the shorter the chain is and the weaker the attractive force is. So melting point, you have a really high melting point if you have a really long fatty acid and if it is saturated. You're going to have a low melting point fatty acid if it's a short fatty acid and one with double bonds in it. Okay? So that's the melting point thing there. Yes?
We have to know about like trans versus cis.
The only thing you do need to know is that naturally occurring unsaturated fatty acids are in the cis double bond form. Trans fats are made through like industrial processes